This is 12.2.2, significance of Young's double slits. So we'll start off with what Newton said in his corpuscular theory. So Newton said that light corpuscles are attracted to transparent medium, and I'm going to use the plural, so media. So they travel faster in them. His theory lasted about 150 years. And was preferred over Huygens' theory. Because A, Newton had prestige. And B, Huygens' theory could not explain rectilinear propagation. Which we'll talk about later. So, after 150 years, we got two main proofs against the corpuscular theory. And these are A, measuring the speed of sound, speed of light in glass. And B, Young's double slit experiment, which produced an interference pattern. So let's compare these together. So Young's double slits. And put on the left side Huygens. And we'll put Newton's on the right side. And we'll start with Newton's theory. So if we had corpuscles which are fired towards or shun towards the double slits, then these corpuscles should pass through these double slits and create two bright fringes. On the screen. So corpuscular theory predicts two bright spots. Huygens theory, where you've got a wave, when it enters a double slit, each slit behaves as another emitter. Now when I draw these, I'm going to draw the wave fronts, and I'm going to draw the peaks as solid lines, and I'm going to draw the troughs as dotted lines. I would change colours, usually, but it will take a bit of time to keep changing colours back and forth. Now, one thing that's going to happen with this drawing, because I'm drawing it freehand, it might get a little bent. But if you did it properly, then everything would line up. But you'll see what I mean in a minute. So we'll start with our first peaks, then the troughs, then a peak, then a trough, and then we'll do another peak, and then maybe we'll leave it at that for now. And then we'll put our screen. So now what we want to do is any point where we've got two peaks meeting, we're going to draw them as, we're going to draw a dot on them. So one here, here, and here. And then where we have a peak and a trough meeting, we're going to draw an X on it instead. So there's one here, one there, and we should have one around here somewhere, but I guess I haven't drawn it very good. Should probably be one there, and there's one there, one there. So what you get when you do this is you get a bright spot around there, and then you get a bright spot there, and you probably get a bright spot up there, a bright spot there, and probably a bright spot down there. And then if you imagined there being dotted lines in between them, so we get bright, dark, bright, dark, bright, dark. So the wave theory predicts bright and dark fringes. Okay, so Huygens liked to draw things. So he's got the Huygens construction. So what the Huygens construction says is that every point on a wave acts as a source for a secondary wave. So if you see when we're doing the diffraction, every point acts like a source for the next point ahead. And if you join up all the secondary points, that creates your new wavefront, and then you do it for the next one, that creates your new wavefront. So every point on a wave acts as a source of secondary waves this predicts where the next wave should be. And your new wavefront is found by joining up the points on secondary wave. So, e.g., we start with the source. Now the source behaves as a source for the next wave. So the first wave front in all directions would be a wavelength apart. So there's lambda. And then when we join them up, this is our first wave front. Then each part of this wave behaves as a source for the secondary wave. And again, these are 1 lambda apart. And then joining all of these gives us the second wave front. And so on and so forth. So we can keep doing that until we get more and more wave fronts. So we can look at some of his drawings again. So if we look at first wavefront and second wavefront, if you make these behave like individual sources, and then you draw your waves, it will give you the location of the next wavefront. As a circular wave, you can do the same as well. And that gives you a second wavefront. So there's your first wavefront and second wavefront. You can think of this as if you drop something in water and you've got circular waves spreading out. Yeah? Now, looking at Huygens' wave theory, it's quite difficult to explain propagation of light other than using his drawings. So there wasn't an easy way to explain how light propagates unless you use his drawings. So Huygens showed how light propagates through drawings. Reflects, refracts, diffracts, and interferes. So all of these things could be explained through Huygens' theory. But corpuscular theory could not explain diffraction and interference. So corpuscular theory could not explain these. Okay, start a new page. So we start with a coherent light source. Then, at the slits, we have diffraction. So diffraction occurs at slits. And there's a small slit separation here, let's say about 0.5 millimeters. And that gives us an interference pattern on the screen with a central bright fringe. So this is all stuff that you've done last year as part of waves. So first thing is, let's define coherent, which means a constant phase relationship. It means that along the wave, the phase between one wave and the next never changes. Now, where we have a crest and a crest, or a trough and a trough, we get constructive interference. So constructive interference occurs when crest meets crest, or trough plus trough. And the path difference is n lambda. Destructive interference happens when a crest meets a trough. And there you've got a path difference of n plus a half lambda. The equation which describes the fringes, W equals to d lambda over S, where d is a screen distance, S is a slit separation, and W is the fringe width. If we want to make fringes further apart, we can decrease S, increase D, or use longer wavelengths of light. So to make fringes further apart, we can increase screen distance D. We can use longer wavelength light. Lambda. Or we can decrease the slit separation. S. Again, this is all stuff you've already done in AS waves. And then we'll finish off by looking at single slit diffraction patterns. So single slit diffraction patterns gives us something called an airy disk. So single slit diffraction produces airy disk. So if we have our wave entering the slit, then on the screen, I'm going to plot this as intensity. So directly in the middle, we'll have the highest peak. Then we'll have a couple of smaller peaks. I might extend this line a little bit. So this is a graph of intensity of what we get. So the central fringe is brightest. And then we've got much less brighter fringes. Now, if you were to actually look at the screen in 2D, so look head on at the screen, you would see it as rings. So if this were the screen, you would have a central bright ring, then a dark ring, then a much less bright ring, then a dark ring, and then you might get a few brighter bits on the edges. So the way I'd like to do this is to use the paint bucket tool to fill in the dark rings, like so. And then to illustrate the fact that the other rings are less bright, I'll do that by shading them in. And then the next ring is much less bright. So you've got your bright fringe in middle, and the shaded fringes are much less bright. So this is called the airy disk. Now, if we were to use monochromatic light, it will give us this sort of pattern. If we were to use non-monochromatic light, for example, white light, then that will produce a central white fringe because all of the different wavelengths will meet in the center. But all the subsequent fringes will be a spectrum. So non-monochromatic. And again, this was also done in AS waves. So central fringe is white. And this is the case for both single and double slit patterns. And subsequent fringes produce spectrum. And this happens because the different wavelengths of light diffract by different amounts. The same way that different wavelengths of light refract by different amounts. So that will instead produce spectra on subsequent fringes. But central fringe, because they all move in a straight line for the central fringe, all the different wavelengths meet in the same place, and that produces white in the center. And that's the end of 12.2.2.